To give a little hint to some of you who are asking questions about the homework assignment, especially regarding the 4 proofs that require induction to do so. So I've started here with problem 111a. I'm just going to plop it down on the screen so you can see what's going on. So there's 2 basic steps when you're doing proofs by induction. The first is you have to prove a base case. That is, you have to prove that the relation is true for some value of n, usually a small value of n like 0, 1, 2, 3, etc. Having done that, then you're going to assert the inductive hypothesis. That is, you'll assert that the relationship is true for values of n of size k or smaller. It's actually technically called strong induction, but it works easily for most cases. And then we're going to try to see if we can use that inductive hypothesis as a tool to prove the thing we're actually trying to show is equal. So let's start here by showing the base case. So for the base case, you want to look here at the value of n. Now you can kind of see here that we have, I said you wanted to start with a small value of n, but obviously you can't start with n being 0 or 1 or 2 because the denominator here, I, goes from 1 up to that value. So the smallest value of n we can work with that makes sense is to have n be 3. So if n is 3, then this will be I will equal 1 up to 3 minus 2 or up to 1 as well. So let's go ahead and write that out. So I'll just go ahead, and my tablet died today, so I have to do this way. Sorry, it's kind of tedious. So every place I see an n, I'll go ahead and plug in 3. So this is going to become 3 minus 2, and down here I'll have I equals 1, and that's going to be of f of I, and we want to know, is that equal to, oops, I lost a bit there, is that equal to f of, again, replacing n with 3 everywhere, so f of 3 minus 2. All right, so that's the question. So this is a base case. I should probably put that in. Let me mark that now. So here we are. This is our base case. Okay. So we want to see if that's true. Now f3, if you think about how the Fibonacci numbers are defined, right? They start at 0. So you have f of 0 equals f of 1. They both start, the first 2 elements in the Fibonacci sequence are always, they start as 1. And the next Fibonacci numbers are always the sum of the previous 2. So f of 2 is going to be the sum of f0 and f1, so that's going to be equal to 2. And f of 3 is going to be the sum of the previous 2, i.e. f2 of 2. f1 is 1, 1 plus 2 is 3. So we have the Fibonacci value, f3 is equal to 3. So if we go over here, we can start simplifying the 2 terms in our base case to see if they're correct. So this is going to become, for the series over here, this is going to be I equals 1 up to 3 minus 2 up to 1. So this is just going to simplify to f of 1. And we want to know, is that equal to f of 3? We just looked at f3 over here. It's 3. So that's 3 minus 2. And we can also see from our definition of the Fibonacci numbers over here that f of 1 is also 1. So you write that is 1 equal to 1. Yes, it is. So the base case holds. So our base case is going to be that n equals 3. Okay, so now we can move on to our inductive hypothesis. So the inductive hypothesis is that we assume that the relationship stated, that's this guy up here, holds true for all values of n of some up to some k. So k could be anything. We know at least k can be 3 because we just showed the base case is true for that. So we'll simply we won't give it a name, let's call it k. So we'll go ahead and we're going to rewrite this, our relationship up here, but every place we see n, we're going to plug in k instead. So then this is going to become the summation, the series of k minus 2, sorry, it's k minus 2. And down here we'll still have our I equals 1. Still have that, right, of f of I. And this whole thing, this is our inductive hypothesis. We say that's going to be equal to f, and again, every place you see an n, we're replacing with k. F of k, whole thing minus 2. All right, and this is right here, I'll mark here, this is our inductive type it correctly. Hypothesis. That is, we assume that our relationship holds for all values of n up to some k. So now we're going to see if we can use this thing as a tool to prove the general theorem. So let's go ahead and we're going to restate our theorem here. And basically out of here we have, here's our general theorem up here. So now we want to use this tool to show our theorem holds if for k plus 1. So every place, basically going to take our formula up here again, and every place there's a n, we're going to replace it with k plus 1. So we'll go ahead and we'll start doodling here again. Let me just grab this whole thing. So, okay. So what we want to do now, instead of every place we see a k, we're going to replace it with k plus 1. So we're going to make some changes here. So first get out of that. So this is going to go from k minus 2, it's going to become k minus 1, because replace k with k plus 1, you're basically changing this to be a 1. So add a 1 there. Put my pen back on. So that becomes k minus 1. This all stays the same because there's no n's in here. So I'll go over, no more k. So over here, I have this k has to be replaced with k plus 1. And just to remind myself I haven't proved this yet, I'm going to put a little question mark on here. Say, are those in fact actually equal? Because I haven't shown that yet. I assume the inductive hypothesis, which is here, but I haven't shown that this relationship holds as well. So that's the next step. Now, the usual trick when you're doing these inductive proofs is you want to make use of the inductive hypothesis as a tool. So one way to do that is to try to change one of the sides, like say this side over here, to look like this side somehow, or change this side to look something like this side. So I'm going to do the first thing. I'm going to see if I can sort of rewrite the left-hand side here so that it actually involves this term over here. See if I can do that. This is sort of a standard trick when you're working with series like this. So one thing you might want to do is think about what these series actually represent, what the summation represents as a series. It may make it a little clearer to you as to what's going on. So let's look at this term over here. What is this if you actually wrote it out by hand? Well, it would be f of 1 plus f of 2, and then plus f of 3, and so on. So let's say dot, 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 plus, right? And then it's going to go up to f of k minus 2 plus f of k minus 1. All right, so that's what this term over here, this summation, actually looks like if you wrote it all out longhand like that. Now the term we started up with in our inductive hypothesis was up here, and that's the same sequence, but it stops here at this penultimate element at fk minus 2. So what we want to do is try to rewrite this left-hand side so that it actually involves this term over here. And can you see how to do that? Right, this part over here, this left term here, I'll just go ahead and highlight them so you can see. This stuff here is exactly equivalent to this expression over here. All right, so I can rewrite this series over here to instead look like this. In fact, I'll just copy this to save some of the typing or writing. So I'll copy that. And I'll put it over here, see if I can get it to move. There we go. So this left-hand side is the same as this, plus the term that I left off over here, right? Because this stuff over here up through k minus 2, that's this expression here. So I put it down there. So then all that's left is this last term here, f of k minus 1. Terrible k minus 1. So same question. Oops, undo that one. Is that all equal to, I'll keep all this. So I basically just took the left-hand side over here and I rewrote it in this form. It's the same thing. So I'm asking the same question. Is this left-hand side equal to this right-hand side? Okay, now that we've expressed our relationship this way, The whole reason we took the time to try to reformulate this, the left-hand term over here, and make it look like the left-hand side of our inductive hypothesis is so that we could apply the inductive hypothesis. Remember, we wanted to use it as a tool. So we can apply our inductive hypothesis here and replace this term over here. Let me just select it so you can see what I'm talking about. Oops, wrong one. So we can replace, still the wrong one. So that we can replace this term over here with this side over here, because that's our inductive hypothesis. So we would write as a proof, we'd say, by the inductive hypothesis, we replace this left-hand term over here with the right-hand side of our inductive hypothesis. We already said, yep, that's true for K. So then the left-hand side, that's these elements here. Let's grab that. I think I'll grab the whole thing. And I'll drag it down here for further doodling. And so this stuff here, I'm going to replace now with the right-hand side of the inductive hypothesis. So I'll just go ahead and grab that. Put it down there. So I'll plug it in like that. Okay. And now I think you can probably see what's going on, right? So from here on, see if you can prove that the rest of this, the two sides of this equation are actually true. And then you can move this little evil question mark up here and state, yep, that's true. So again, the keys were we rewrote one, or sometimes we rewrite both. In this case, we rewrote one of the sides of our the theorem we were trying to prove, one of this equation, this relationship. We rewrote it in terms of things that had already been mentioned in our inductive hypothesis. We then applied the inductive hypothesis. And then from then on, you just have to show that the rest is true. Once you've shown that, once you've got that done, you can say, QED, I have demonstrated the equivalency through induction. So I hope you found this hint useful, and I'll see you in class.